So I will talk to you about a very simple bench, measurement bench, but I guess some experiment here could be useful for your technician in your lab. So the title is Automatic Vector Signal Generator Calibration Method Suitable for Multiport Large Signal Measurement. So first of all, I would like to talk about very basic measurement with power sensor in CW mode. So basically what we do, we define a reference plane, here displayed in red, and we have two power sensors, right? One for the input, one for the output, and we just have to identify an offset between our power sensor and that reference plane. This is for basic CW measurement. If we want to do modulated signal measurement, then the source is not CW anymore, it's a VSG, where we drop in the ion Q data. And the receiver usually is a one-channel VSA, where you can measure the input and the output sequentially. Okay? And if we want to calibrate the source, basically the calibration of the source, not calibration in terms of measurement accuracy, we will measure with the receiver, but just in order to know approximately the level here we want to apply in terms of the source. So we need to know, according to the calibration between the instrument here and the DUT, what is the power offset between the command and the DUT reference plane over there. So I will talk about that during all the presentation. So usually this is the setup that everybody uses with a single VSA. And if we are connecting the device like that, usually there is some unknown on the measurement of the VSA, that is the delay of the envelope and the phase of the local oscillator. And these unknowns are a pain in somewhere, and we need to apply some complex algorithm to perform the time domain alignment. But if we synchronize correctly the VSA and the VSG, this time domain alignment, we don't need to do that finally. So we need three synchronization. We need the 10 megs in order to, that is the reference signal from like the time base, indeed. We have the trigger to be connected between the VSG and VSA. It will give us the start, synchronous start between the VSC and the VSG, and we need the local oscillator connection here. If we perform this local oscillator connection between both, this kind of setup can give you a measurement of the MPM. Without that, if you want the MPM, you need a time domain alignment software. So this is the current measurement input-output. But now, what will happen regarding PA's design right now? So the most popular PA right now is the Doherty, displayed here. And another one is coming since few years is the LMBA. So basically, everybody knows the Doherty, I guess. You have a main amplifier here, and you have an auxiliary amplifier, and basically the idea is to move the load impedance of the main dynamically. So the change of this impedance seen by the main is produced by the auxiliary amplifier in class C. The LMBA, if some of you don't know that, basically the principle is the same. So it's a dynamic load modification. But this time, it's like a Doherty, but isolated. So the load, indeed, is produced by injecting a signal here. And we have two mains. Here it's 3 dB 90-degree couplers. So you have a phase offset of 90 degrees here. So the loads produced by the injection here will be 90 degrees offsetted here. So the two PA will work exactly in the same way. So if we have this kind of PA right now we want to measure, and if we consider that the digital world is coming to us pretty quickly, this area over there could become digital very soon. Sometimes it's already digital. So what happened is the power circuits over there that are not digital, that can't be digital for the moment, the dot of interest here in the analog world, finally we should consider that as a dual input PAs, as well for the Doherty PA or the LMBA. And we can consider the RF path before like a digital control. So this is the context of my presentation. So I will talk about the calibration of the source, I told you, that could work both for CW and modulated signal. So first of all, I will talk about the one-port calibration, that is pretty obvious. Then I will extend this one-port calibration to a multi-port calibration. And I will apply this algorithm to two kinds of measurement, one on the digital Doherty measurement and one on the LMBA measurement. So if you want to do one-port calibration, in CW, this is pretty obvious, I told you. You just have to put a power sensor in the dot reference plane. And here, you just have to change the power level of the source, and you can identify the offset, whatever the driver here, between your command and what you have in the dot reference plane. All right? So this gives you a power offset that is basically the gain between the command of the instrument and what is available in the dot reference plane. If you want to do such a power calibration with a VSG, usually we fix the local oscillator, but as the power sensor is a standard, is a power standard, we have to measure in CW. So basically the idea is to sweep a CW complex envelope in digital I of t and Q of t here. We sweep just the frequency inside of the envelope, and we measure with the power sensor what is the power here, so we can get the gain between the command and what is available in the dot reference plane. And if we want, oops, yeah, it's slow indeed. If we want to perform a phase calibration of this gain, so obtain the phase of this gain, the only way for the moment is to use a calibrated VSA in the reference plane, apply a multitude signal. We know the phase of all these tones here. We measure something in the dot reference plane, then we can identify the phase of the gain between the command, digital command, and what is in the reference plane. And for such calibration, we need the tree synchronization. All right? But from this, we need to extend that to multi-channel. So basically, according to the fact, we know how to calibrate one source between one command and the dot reference plane. We will see how to increment the number of sources if we want to measure a multi-port signal, multi-port dot, sorry, and to make the calibration pretty easy. So let's consider SNP. So if we want to characterize a dot with a lot of input over there, the dot, the calibration standard will be a passive device, N port, like this, that has been previously measured with a VNA. So it could be considered as a standard. And all the measurement for the calibration of that will be power sensor. That is a power standard as well. So we consider the first channel as already calibrated, like I presented before, and the other channel will be calibrated automatically, and each channel independently. So for example, here the channel 1 is always on during the calibration, and one of the other channel will be only one of the channel will be active. The other one will be passive. So this kind of structure at each step of the branch we want to calibrate will be like that, with only, it's weird, will be like that. So we have the channel 1 always on, the channel I on, and the other one, because of the circulator, will be considered like 50 ohm. So the idea is considering this channel already calibrated to identify the gain here in magnitude and phase between the command of the instrument and what is really available in the reference plane. So if we just write the S parameter equation of the SNP we already know, and the power, the output power we measure here, we can extract a quadratic system that we can linearize like this. This is just a linear equation, finally, where we know all the terms. And what we are looking for is this gain, complex gain, for each frequency, magnitude, and phase. And to identify this gain, we need to have 3 independent measurements. So we will change the phase of this signal thanks to the IQ signal here, compared to this one that does not change. Okay? So a minimum of 3 phase position will be enough in order to identify GI here. You can do more. It will be a least square solution of GI. So basically, we apply, if we use a VSG, we can, in CW, we can apply a constant envelope IQ here, and here there will be a constant envelope IQ, but we will change the phase between the I and Q. And from this value, from the output power measurement, the SNP parameters, we have all this data over there. We can fill a matrix, and we can obtain the gain, complex gain of each channel like this by just reversing a linear system. Okay? So that gives us a way to identify the source, the gain between the command and the dot reference plane. So when you have a system where you have, for example, 5 channels at the input, with just one SNP, an automatic procedure will give you the calibration of your source. So let's check this calibration with another SNP. For example, I use here a 2-channel VSG over there, and I check with a SNP, a combiner, a power combiner here. And I will present here, so basically I will change the phase here of the RF, so the phase of the constant IQ of the second channel. It's like if you change the phase of the LO on the second channel compared to the first one, and measure, of course, the output power. I will present 3 curves. One, if we do not calibrate in phase the system in the reference plane. One, when the phase is calibrated. And the third one in red, is the simulation. So the simulation is taking into account the output power at the output here, and taking into account the S-triple parameter. We can deduce, calculate by simulation, the phase of the second channel compared to the phase of the first. And the results are here. Here's an example where we sweep from 2.2 to 2.8 with a 100 megs step. If we do not calibrate in phase, you obtain the blue curves. And it moves a lot. Why? Because at different frequency, the time group delay of the second chain is not the same. If you calibrate the system, as I told you, you obtain the black lines that totally fit the simulation. All right? So now I will illustrate that with dual input power amplifier. The first case is a digital Doherty. And with this kind of setup, calibrated in magnitude and phase, you can find the best control rule at the 2 input in order to optimize linearity or efficiency. So you can sweep as any PA the power at the channel 1, and for the channel 2 you can sweep the power and the phase. Get a lot of data like this, and from this bunch of data you can extract what is the best command law, in this case for the maximum PAE, or the best command law for a good linearity, so here to extend the linear gain over there. So basically here, at the end, this is the load. Delta P is the offset of power, and delta phi, the offset in phase between the two channels. We can do the same with the LMBA. So I'm not a designer, so I did an LMBA with some Lego bricks, about 2-3 amplifiers, 2 3 dB couplers, and I measure this stuff that is absolutely not optimized. And this is the kind of graph we can obtain. For example, for one output power, for one input power at the first channel, we can trace directly a complete graph of delta P, that is the power of the second channel, and delta phi, that is the phase compared to the first channel, and obtain directly the graph, just with a power sensor, of output power, the black lines, and PIE, that is the color on the graph here. And I remind you, it's just a power sensor setup. And that's interesting for the LMBA, for example. You can find out where is the optimal PIE or the optimal Pout. And if we select a point over there, this point, in the case of an LMBA structure, give you directly the AMAM or AMPM of the extra branch you need to design between the input and the port where you want to inject the signal. So that's it, very quickly. I hope it will be useful for some of your engineers. So here's a calibration method that could be totally automated. You need, I didn't say that, you need to consider a single LO in all your setup and manage even for CW IQ envelope. It will make it repeatable. And I illustrated with LMBA and Doherty setup. Thank you.
We have time for a quick question or two. I had one. In your calibration, you have the SNP block. Is there a preferred implementation for that? Is it just an N-way combiner?
It could be anything. It works? Yeah. No, it could be anything. We just need to know the S parameter. But the advantage is when you automate the setup.
Automatically.
Whatever so it goes very fast because you can have a lot of channels instead of measuring the power at every channel or even the phase. It's not obvious to measure the phase if you don't have a VNA. Here it's a setup where there is no VNA usually. So you already have a small SNP. And with just that, you can consider it's a standard because it's already measured with a VNA. The output power is a standard, so you can calibrate all your bench.
Yeah. Okay.
So as a user experience, it's one click, and you select your frequency of measurement before. Okay? It's repeatable because your source share the same local oscillator. So in one click, you calibrate a complete setup, whatever the number of source.
Is there a problem if you have, you say you have a lot of parallel paths of is a lot of loss affecting the quality of your calibration?
I think yes, it's the loss increase, but I don't know. I guess not a lot of people measure 20 input PAs.
Fair enough.
But I experienced just for a dual input that is interesting right now, and it works pretty well.
Thanks. Any other questions from our audience? No? Well, let's thank our speaker again.